we are looking at many different things at simulation. So for sure we want accuracy, but at the same time we want to calculate the things in a reasonable time. Through the recent changes and speeding ups of 5 to 10 times, it has completely changed the way we are doing simulations. The first biggest impact was that we didn't have to invest in huge hardware because of the cloud-based simulation. We can easily see it by measuring the temperature of the bearing, and we know if the temperature is rising more than the other parts of the gearbox. We don't know whether there is oil or not because you can't look through them, and now you can see the results. You can get much better results.
All right, ladies and gentlemen, Andreas, welcome to the show.
Thank you, Jousef. I'm very glad to be here.
Really cool. So in the past podcast episodes, we talk a lot on this podcast about the theoretical aspect of simulation, right? And today I have an expert in the show, namely Andreas, who wants to talk about how it's being done in the industry. But before we jump into that, what tools you're using, what methodologies you're using, can you give us a little bit of insights? Who are you in the first place and what are you working on?
Yeah, thank you very much. My name is Andreas. I'm a mechanical engineer and I have studied at Karlsruhe University. And now I'm working at company who is called Kessler & Co., which is producing axles, gearboxes, and so on. And I'm working in the field of computational fluid dynamics, and especially I'm working with SPH, so a particle-based method.
Mm-hmm. How did you first get in touch with simulation? Because I would be interested in why are you so fascinated about CFD? Why not FEA?
I got into the topic through my PhD studies. So I'm working on a PhD and I'm looking into losses of gearboxes, and we have realized that a lot of losses are coming from jamming losses and splashing losses. And that was the first reason why I came into CFD.
Yeah. I'm wondering, when you were studying at uni, because I know it from my perspective, we studied at the same university, by the way, which is funny. How are you approaching the choice of simulation or simulation types? I don't know, fluid, like volume methods, SPH, you mentioned there's different types of methods. How do you decide from a theoretical point of view which method is the best? And then from an industrial point of view, which one is the best, but then also taking into account savings such as resource savings, etc. I think there's different objectives, whether you're working at uni versus when you work in the industry. So maybe to answer the first question, like what are you looking for in a simulation?
Yeah, I mean, we are looking at many different things at simulation. So for sure we want accuracy, but at the same time we want to calculate the things in a reasonable time. And what we see for simulating the gearbox is that we are very much limited when we are using mesh-based CFD, because we can't simulate it. The gearboxes are simply too big. The oil volume is simply too big. And that's why we came into CFD. Why we came into SPH, and we are using SPH now for both at the university and also at the industry.
Mm-hmm. Can you share maybe the specific tool name that you're working with?
Yeah, sure. We are working with Dive. We have used several different tools from the SPH field. At the moment, we are using Dive, which is very easy for us to use because of its cloud-based computing.
Yeah. Dive, by the way, I know the owner, or like one of the CEOs, Pierre Zabrowski. I also had him in the podcast in the past, like I think 2 years ago. Why have you made the choice going down the Dive path? Because I mean, we have finite volume methods, etc., as we just discussed. Why SPH in the first place? I mean, there's several tools that are also cloud-based, but there's clearly something about Dive that made you choose Dive and not some other tool.
Yeah, so it was actually the accuracy we got out of the simulations. The simulation results were matching our test bench results the best. So we are doing a lot of tests at the company, many different gearboxes, many different settings, and so on. And we compare the results from different tools, simulation tools, and it was that Dive was giving us the best results. That's why we are using Dive.
Yeah. In the same amount of time, would you say you can run now more simulations as compared to other methods that are out there? What other impacts or benefits do you have using Dive?
Yeah, absolutely. So the first biggest impact was that we didn't have to invest in huge hardware because of the cloud-based simulation. And then, of course, it was fast, and you can't compare it with mesh-based methods. It's so much faster. And now, even in the recent time, the GPU solver came out, and the GPU solver is giving us again 5 to 10 times speed ups, which is incredible, and which is changing our daily work so much, and how we are using CFD or SPH in general, and it's giving us also the huge impact to, or Dive is giving us the huge impact to simulate not just one simulation, but to run several simulations on several different instances. So this is giving us great opportunities.
Yeah, this is really cool. I mean, I've been in the simulation field probably not as long as you, Andreas, but everybody talks about we are faster, we are more accurate, etc. But you talk about 5 to 10 times faster. If you make it more concrete in terms of timelines, do you go from weeks to hours, or do you go from hours to minutes or seconds? How does it look like in terms of timescales?
It's depending very much on the simulation. So I would say for a typical axle or gearbox from the industry, from Kessler and Co. Before we were running probably 6 hours, and now five times faster. We are running often under 1 hour. So this is a huge impact. But then we also simulate. We have big simulations which were running before 2 to 3 days, which have come down now also a lot. So it's both. We run medium-sized simulations. I think the simulations which are running now 1 hour, they are still kind of big for the industry. Yeah, and then we run very large simulations which have decreased a lot.
Yeah. Walk me a little bit through the workflow, because I think from an academic point of view, it's just like you run the simulations, you evaluate them yourself, you don't have a team or other departments waiting for the results. How does it work? I think that would be interesting for the audience to know. How do you work with other departments who are maybe not simulation experts, and how do you communicate the results internally? That would be interesting to understand.
Yeah, so it's on the daily basis. It's like this, that my colleagues, they are coming to me and they are saying, I have here a special question. For example, I don't know whether the lubrication of this bearing is enough, or whether the seal is getting any oil or not, or if there's too much oil and is generating too much losses. Then I look into it. I get the cut data from my colleagues. Then I'm doing some pre-processing, but the pre-processing is limited to combining for example, the parts which are moving at the same speed. Yeah, and then I take the STL data and drop it into the Dive software, and set my boundary conditions, and then it's runtime.
Yeah.
Yeah, and then
In the post-processing, sorry for interrupting, in the post-processing bit, how do you evaluate the results? How easy is it for you to evaluate the results and send it to other people who might not be experts in simulation?
yeah, I mean, the best thing is to see where the oil is moving. So when I'm discussing with my colleagues in the first place, it's always, is there moving here? Is there oil here, or is there an oil? And if we are doing tests on our test benches, we don't know whether there is oil or not, because the gearboxes, they are not, you can't look through them. Yeah, and now you can see the results, and the colleagues, they just either come to my desk, or I go to theirs, and we share the screens, and we discuss where the oil is. So it's very easy, and it's very easy to understand. And also the usual engineers, when they see the result, they often already know what they have to change in the system to do it better, to make it better.
With changing in the system, you mean they go back to the CAD model, make some adaptations, and then you basically rerun the simulation. Is that right?
Yeah, that's right. Or it's depending. So if there are just very minor changes, I sometimes do it by my own, but mostly the colleagues are doing it. yes, and then rerunning the system is fast, and you get soon the results.
Yeah. I'm wondering, because you were talking about the test benches in the beginning, how do you make sure that you have the accurate boundary conditions inside of Dive that are representing the real world? So how do you ensure that in the industry? How do you do that?
Yeah, I mean, we do quite extensive testing, and we do it for special projects on a very large scale, or we dig very much into it. And then for other projects, we know from our reference projects how do we have to handle it. So what we are measuring is always temperatures at different parts, and then of course the losses and so on. Yeah.
How do you validate that? So, for example, if you have a simulation, how do you make sure that the simulation matches kind of the experimental results?
Yeah. So for example, for the questions whether there is enough oil at a point, so that for example bearing is lubricated enough, we can easily see it by the by measuring the temperature of the bearing, and we know if the temperature is rising more than the other parts of the gearbox, there is not enough oil, and so we know whether there is enough oil or whether there isn't enough oil. And we have some cases where we where we have seen before that the bearing is, for example, getting hotter. We run the simulation, we see there is no oil there. Then we change the CAD file, we run again the simulation, we see the oil is there, and we try it again on the test bench, and we see that the temperature is not rising anymore. So we are very sure that the simulation and the test benches, they are on one side, and if you do it for some project, you know that for the other projects it will work as well.
I see, that makes sense. That's super cool insight, Andreas. I'm wondering, from a product development point of view, like when you front load the product development process using Dive, I mean, we talked about the time savings, but how, for example, does the dynamic inside of the team change? For example, you are able to communicate faster between departments, but also how does it affect your product that you then deliver to your customers? Do you get any feedback from your customers?
Yeah. So for the first question, through the recent changes and speeding ups of 5 to 10 times, it has completely changed the way we are doing simulations, or it has quite immensely changed the way we are doing simulations. So we are doing much more simulations. For example, we are running more operational points, more different speeds, more different temperatures. And before we were limited very much, but now when the simulations are running faster, you can do more simulations, and therefore you can be sure that you have tested the product over a wide range of operation points, and therefore you can simply make the product better. And then a second point is that we are doing much more iterations for designs. So before we have one design, you run the simulation, you wait until it's finished, and then you do a change, run it again. But maybe you have time for probably one week, and it's just limited how many simulations you can get through it. But now you run a simulation, and even like after 1 hour, you have the result. You can do the changes, and now you can run probably 6 iterations per day, which is giving you a much better result, or the product can be generated in a much better way.
I think clearly there is some competitive advantage that you have compared to other people in the industry. How do you envision that now with the faster simulation using Dive, how this will elevate your reputation in the market, like for Kessler, I mean the company Kessler?
I think that the biggest disadvantage is that we can expand our product, or that we can go into areas which were difficult for us before. So if you know how the oil is moving inside, and you can do many different variations, you can get much better results, and you can be sure that it's working much better. And sometimes it's the best thing is that if you are seeing what the oil is doing, you can make it even simpler inside. You don't have to put another oil pump inside or whatsoever, and therefore you can make a more robust product. Our products, they are very, very robust, but you can even improve it. So that's really a big advantage for us.
I like that you talk a little bit about the product quality, because as we all know, the German automotive OEMs, they're struggling a little bit. They have to let go of a lot of engineers, and at the same time, they have to make sure that the product quality stays the same or even gets better. So talk to me a little bit more, maybe a couple of minutes, about the product quality. So how does it actually or explicitly improve using simulation methods? You talked about the oil pumps, for example, but how does the overall product quality improve using simulation? The right type of simulation, I should say.
Yeah. So I think the biggest challenge is that if you want to make a product really better, you have to understand what's happening inside and what are the effects behind. And if you don't know them, if you don't understand them, you are limited in how good you can make the product. So if you get insights into topics where you couldn't get insights before, this is making a huge impact. So, for example, if you know how the oil is moving and you can make the oil flow better, it's giving you a huge impact. But also, for example, we are looking into bed disc brakes, and now if we can see how different designs is changing the cooling of the brakes. This is also impacts which you can't get without any simulation. And then, the question is, what is the right simulation tool? And to answer it, you have they have to be the same, or the accuracy of the simulations have to be good. But then the second part, and I think it's very, very important in the industry, is that the costs you're putting into it and the time you're putting into it has to be reasonable. And what we see is that with SPH, with dive software, we have reasonable time input and cost input and get great results. And this is improving the products hugely.
Yeah, you don't have to go into the specifics, Andreas, if you don't want to, but how do you actually calculate the ROI? Do you just calculate the manpower spent on simulations compared to other tools? Or how do you actually, like, what do you take into account? We have product quality, time, cost. What else am I missing here?
I mean, costs for the software and also the hardware is, of course, a very important factor. And then also I think more how many and how good results can be done by one person. It's quite important.
Yeah, which brings us to the aspect of parallelization, right? Like, how many simulations can you run in parallel using Dive? That would be interesting to know.
I think I have never gone to the limit.
Okay.
But I have run many simulations at the same time, and this is giving huge opportunities. And running many simulations at the same time is can be quite challenging if you don't do it right, or if you don't have the right tools. So what we are doing, or what I am doing, is I'm using quite heavily the Dive API, and I'm scripting all my simulations with Python.
Nice.
So for the different operation parameters, for example, I just have my standard script, and then I adjust the operational points. And also for the post processing, if you have many simulations and you run many simulations, but you don't post process them, it's nothing worth. So also for the post processing, it's very much automated on our side, and this is giving us huge opportunities. And then we have been talking before about academia and uh, and industry. And I think for industry, it's quite interesting to run more operational points, more iteration, more design iterations. And then for academia, it's more interesting to run more like boundary conditions and settings and so on. So it's different, but on both at both times I'm running quite many simulations in parallel.
That's really cool. In terms of post processing, I believe Dive already has an integrated post processor, right, where you could just see the results in real time.
Yeah. It has an integrated post processor also with sensors and so on, which you can script, and then you see the results in real time or nearly real time, and then and then if you want to dig quite deep into it, there are other possibilities.
Yeah. I'm not sure if this is strictly confidential, but can you talk a little bit about cost savings, explicit cost savings that you have achieved using simulation CFD, or in this case, Dive?
Yeah. So it's a bit difficult to calculate really the cost savings. What we see is that we can get better products, that we can save time in testing because we know that the product is good. I can't give you any explicit numbers, but the impact for us is huge.
At least I tried, but thanks for giving us the insights. One of the mantras that engineers have, or that we engineers have, is never change a running system, right? You used some other simulation tools before, and Dive isn't that old from a simulation timeline point of view. How have you convinced yourself, but also your team, to switch from one tool to another, and how difficult was the change?
I mean, using Dive as a software is quite easy. I mean, you have to get to know every software and you have to get to know the borders of every software and so on. That's clear. But through this intuitive graphic user interface and the possibility with scripting, the change was quite easy, and for me as well, for our teams, it was not a hassle at all. So what was counting was the quality of the results.
I see. Looking forward 3 to 5 years into the future, how do you imagine, what other types of use cases or parts will you simulate using SPH, the SPH method, but then using the Dive software?
Yeah, it's quite interesting question. I think what we didn't expect is that we see such a huge speed up this year, and we are at the moment seeing that it's already changing our simulation habits quite a lot. We simulate much more simulations. We do more operation points. We do much heavier simulations. For example, if we are simulating wet disc brakes, they are quite heavy simulations because you have quite some oil inside it, and you have very, very, very narrow gaps, which are significant for the oil flow, for cooling, and so on. And before, it was nearly not possible to simulate it, or it was possible, but it was simulation time several days, and therefore you couldn't do many iterations. Now we are seeing that we can do it in under a day, and we can do iterations. So that's great. And I think further speed ups will be very, very interesting because larger systems can be simulated, and also systems can be simulated with finer resolutions, which is often giving better results. So I think we will get much more insights in the products, and from academia also we can explain effects which are happening because we get deep insights, and I'm looking very much forward for faster simulations, and therefore for much deeper inputs, insights, and much better products.
Absolutely. I'm wondering, maybe this is a very odd question, Andreas, but do you think there is kind of a point of diminishing returns where the simulation could be too fast? What I mean by that is maybe it's so fast that other departments can't even follow up because the simulation is just happening in seconds. Like, do you think that will happen at some point?
I mean, what we are seeing, if the simulation is getting better, is you have the simulation which is running faster, and therefore you have to adapt your pre-processing and your post-processing, because otherwise your simulation is fast, but pre and post-processing, they stay the same, and then you don't get things out of it. So what will be quite interesting is how fast the pre-processing can get, and also how fast engineers can, or my colleagues who are designing the gearboxes can adapt to the things. So I think for simulating gearboxes, at the moment we are not there to simulate like the whole process, like you are doing it sometimes in FVM, and run the system on its own to improve it on its own. For gearboxes, we are not right there yet, but I think we will be there in hopefully shorter than we expect.
Yeah, definitely. One of the last questions I have for you, Andreas, is I think what would be very interesting for the audience. I know we talked about it a little bit in the beginning, but what for you was the biggest change, academia, working at KIT or studying there versus going into the industry? Was there like a mindset shift that happened for you as an engineer, or what changed for you? What was kind of the biggest wow moment for you?
So I think what's the good thing is that I'm working very much in the research part in the industry. So some things are the same. I think the biggest difference is how big the things are, or how many things are influencing each other, and you just can't cut your borders, your boundaries like you do it in academia, and you can make a small box with the simulation, but you have to look at the whole part, because it's so much influencing each other.
Got it. I think with that, Andreas, I learned a lot from this podcast. Is there any closing remarks from your side or any recommendations if anybody wants to try SPH out there? What would you tell them?
I would tell them to get your hands dirty and do simulations, and I think also don't give up too soon. So you have to try it, and then you will have a lot of fun, and don't stop. Try to simulate crazy things, and see where the boundaries are at the moment, and push on the boundaries and the borders. Yeah.
Excellent advice, Andreas. Thank you so much for being on the show. And maybe if we have an enormous speed up in the next coming years or months, then we'll maybe have a second episode of the podcast.
I would love it.
Thank you so much.
Thank you too.